Today, we want to take a break from all the technique that we've been working on. We just finished a 3-day stint in integrating rational functions that went into way more detail than anybody ever needs, except for me, because it's fun. And before we get into trigonometric substitution, which is going to be everybody's favorite, I want to take a quick detour and take a look back on our fundamental theorem of calculus, specifically the second part of the fundamental theorem of calculus, constructing antiderivatives. This is also going to give us an extra day to think about the products of powers of trig functions that are not integration by substitution, so we can sort out what to do with them. All right. So we're going to start with this nice straightforward problem. I'm going to define a function f of x with a bunch of line segments, and we're going to define a function capital F as a definite integral from 1 to x of f of t dt. So let's note some of the things that we want to see about this. First of all, I'm using a definite integral to define an antiderivative. So from the second fundamental theorem of calculus, capital F is an antiderivative of little f. So from second fundamental theorem of calculus, capital F is an antiderivative of little f. That is, capital F prime is little f. So over in the image, we have the graph of little f. And we want to note that this is the graph, also the graph of capital F prime, the derivative of capital F. What this means is that we want to read this graph as a derivative. So we can read this graph as a derivative. We know that when the derivative is positive, our function is increasing. So when I talk about reading the graph as a derivative, that means noticing that when I talk about reading the graph as a derivative, that means the sign of the derivative indicates the direction of the function. Sign of the derivative tells you about the direction of the function. In addition to reading the graph as a derivative, the direction of the derivative tells you about the concavity of the function. Oh, these go both ways. The direction of the function will also tell you about the sign of the derivative. Another piece of information that we have is that the direction of the derivative will tell you about the concavity of the function. This is what we mean by reading the graph as a derivative. The sign of the graph will tell us the direction of the function. Sorry, the sign of the derivative will tell us about the direction of the function. the direction of the derivative will tell us about the concavity of the function. This is just going way back to when we first learned about derivatives and intervals of increase and decrease. So when the derivative is positive, that tells you that the function is increasing. Now, once we got to definite integrals, we refined this idea a little bit more. So we get some additional information. So the sign of derivative tells us about the direction of the function, and the area tells us how much increase and decrease. So in addition, the area tells us the amount of increase or decrease. Let's take these ideas and apply them to the graph that we're looking at, the graph of f prime, and see what it tells us about f, capital F. So notice that this graph of f prime, capital F prime, the graph of the derivative is negative on the interval from 0 to 2 and also from 5 to 6. So f prime is negative on the interval from 0 to 2 and the interval from 5 to 6. So this tells us that our function is decreasing on those intervals. Then from 2 to 5, the derivative is positive, so the function is increasing. Moreover, when the derivative is equal to 0, that means the function is flat. That's an extra detail that we should be looking for. Just use function notation. Everything's in function notation. Why not use the function notation? So just based on the graph, f prime of 2 and f prime of 5 are equal to 0. So at 2 and 5, f prime is neither positive nor negative, so the function is neither increasing nor decreasing. I usually describe this as the function being flat. At these 2 points. We can refine this a little further because we have such a good picture. Notice that the function changes from decreasing to increasing at 2. So if we change from decreasing to increasing, we have a local minimum at 2. And then we change from increasing to decreasing at 5. So we have a local maximum at 5. So combining this information with the stuff that we already know, we can refine this a little further and say capital F has a local max at x equals 5, because we've changed from increasing to decreasing. At x equals 2, we can say the capital F must have a local minimum because we've changed from decreasing to increasing. So we're getting a lot of information about our function based on the derivative. We've identified intervals of increase and decrease. Since we have such a clear graph, we can figure out how much increase and decrease we are getting by looking at the area. So if we break this down into just rectangles and triangles, which is why I use line segments in the first place. If we look at the amount of increase between 2 and 5, from 2 to 3, we have an area of 1, so we have an increase of +1. From 3 to 4, we have an increase of 2. And from 4 to 5, we have an increase of 1. So F increases by 4 on the interval from 2 to 5. Because the area tells us the amount of increase. And then the area can also tell us about the amount of decrease on the interval from 5 to 6. I can mark the definite integral as -1. So F decreases by 1 on 5 to 6. And on the interval from 0 to 2, F is decreasing by 3. Decrease by 2 from 0 to 1, and decrease by 1 from 1 to 2. This is just using our first fundamental theorem of calculus. The area between 2 and 5 of capital F prime of x to x is equal to F at 5 minus F at 2, which is equal to 4. If F of 5 minus F of 2 is equal to 4, that means capital F has increased by 4 on the interval from 2 to 5. Similarly, for 0 to 2 and from 5 to 6. Any questions? Trying to build a picture by identifying everything that we can read from the derivative. So let's go on. This is a lot of information that we've acquired from the, we can actually compute values. Let's compute values. So we can actually get a lot of information based on direction and amount of and increase and decrease. Looking at the derivative, we get a lot of information about how much the function is increasing and decreasing once we throw that area part into it. So let's make some calculations. Let's complete a table of values for the function capital F. So let's plug in, have some x values and some capital F of x values. So we should note we're looking at the derivative. So we've taken the derivative. That means the derivative of the constant was 0. We don't know where to start. We just know how much things are changing. So all we know is how much things have changed. So based on the graph, from 0 to 1, whatever these values are, we have decreased by 2. And then from 1 to 2, we see a decrease of 1. So based on just the graph, we know how much things have changed, but we don't know where they started. We need something to tell us about the plus C. Just based on the graph, we don't know the plus C. So we should note, just based on the graph, we don't know where things are vertically. From an integration standpoint, we don't know what the plus C is. We have to have an additional piece of information we don't get from the graph. The graph just tells us that we drove 400 miles. It did not tell us where to start. But if we go back to the original definition of capital F, the original definition of capital F is the definite integral from 1 to x of f of t dt. And so that contains information about where to start. In particular, it gives us a place where the function is equal to 0. So there are two ways that I could tell you about the plus C. One is I could just tell you one of the values of f. I could say f of 0 is equal to 0. That would give you a place to start. Or I could be specific about how I define the function with our second fundamental theorem of calculus. I can be specific about how we construct our antiderivative. So we're defining capital F as the definite integral from 1 to x of f of t dt. The reason that it's f of t is just we want a different one than the one we're plugging in. We don't want to plug x into f of x yet. It would work out just fine, but it becomes like a bean John Malkovich kind of situation, so we won't do that. So we just put in a stand-in variable t. So we get a 0 based on the definition of the function. If we plug in 1, if we appeal to the original definition of our function, capital F of 1, that's the integral from 1 to 1 of f of t dt. And no matter what else goes on, no matter what else is going on in the function, that tells us where to start. Because f of 1, if we integrate from 1 to 1 of f of t dt, we will definitely end up with 0. Regardless of whatever else is going on with the function little f, integral from 1 to 1 will be 0. So that's how we got the information of where to start. Once we know where to start, we can just use the changes to figure out the rest. If we start off at 2 and decrease by 2, we'll end up at 0. We decrease by 1. We increase by 1. We increase by 2. We increase by 1. And then we decrease by 1. Once we have a place to start, we just follow the changes till the end. Once we get a key to start in, we'll just follow the changes. This is such a basic calculus problem. Whatever the starting value is, thinking of the changes, this is definitely a 1, 5, minor 6, 4. Most definitely. There's another piece that we could read based on the derivative that we haven't used yet. We've got all the values. So if we were going to try to draw this graph, we know exactly where to put all the points. So actually, let's go over here and draw that. So we're just going to start by plotting the points. Need to go up to 3. So it's going to be 3. Two, 1, 0. Only goes down to -1. So I'll just shift this whole thing down. So we could start just by locating where the graph is. F of 1 was 0. And then we had changes after that. So start off at 2, drop down to 0, down to -1, back up to 0, back up to 2, up to 3, then down to 2. 1, 2, 3. So we just need to connect these dots. We want to be careful about how we connect these dots because we have more information. We also can see the graph of the derivative, and the graph of the derivative has direction. Once we know the direction of the derivative, we can determine the concavity of the function. So we want to think about the concavity of the function. The direction of the derivative tells us about the concavity of the function. So we can see on our graph, I just smeared the graph, didn't I? Ah, no, good. We can see that our derivative is increasing from -1 to 3. So our function will be concave up from -1 to 3. So capital F prime is increasing on the interval from 1 to 3. So capital F is concave up on the interval from 1 to 3. That makes sense. That fits with the local minimum that we're supposed to get at 2. At 2, we see our function, we had a local minimum. So we should see concave up at 2, and that's what we see. The other thing that we note on the graph is that our derivative is decreasing on the interval from 4 to 6. So our derivative, capital F prime, is decreasing on the interval from 4 to 6. So that tells us capital F is concave down on the interval from 4 to 6. That fits with the local maximum that we're going to be trying to draw at 5. On the other two intervals, from 0 to 1 and from 3 to 4, the derivative is neither increasing nor decreasing. The derivative is flat. The derivative is flat on the interval from 0 to 1 and from 3 to 4. And that's going to tell us that the function is linear on the interval from 0 to 1 and 3 to 4. When the function is flat, or when the derivative is flat, that means it's neither increasing nor decreasing. Which means we have linear, because linear is neither concave up nor concave down. So we're going to draw a linear graph from 3 to 4 and from 0 to 1. We're going to draw the graph concave up on the interval from 1 to 3 and concave down on the interval from 4 to 6. We're also going to want to make sure that the graph is flat at 2 and 5. Now we have a nice detailed graph based on the blue. And it fits all the description that we had before. All the points are in place. So the amount of increase and decrease that was given in our graph the derivative. So we knew where it was increasing and decreasing, by how much it was increasing and decreasing. We knew where it was flat, and we knew about the concavity all the way through. Any questions? I try to be a little bit careful about where things are positive and negative, so I was using open intervals. Because on the graph, the derivative, at the point 1, it's hard to say. We aren't able to say. There's a corner there on the graph, so I can't talk about what's happening at 1. I did use closed intervals around 0 and 6 because I was talking about where the graph was positive or negative. So it made sense to say f prime was negative when x equals 0 because it is. And similarly, it's 6. But when we're talking about increasing and decreasing at a point, those points are at corners, so we can't talk about direction. Specifically because it goes from increasing to flat. If it went from increasing to just differently increasing at the corner, then I could probably include it and say that, but it would still be a little bit tricky. Up next, we'll discuss the products of powers of trig functions that are not substitutions and how to deal with them. Once we get this sorted out, only then can we start talking about trigonometric substitution. And that's going to be our favorite. That's going to be our favorite substitution. Remember, some integration by substitution is the easy one. That's why we're going to love trigonometric substitution so much. It's just a substitution. How bad could it be? People that watch a lot of Top Gear will recognize it could be pretty bad. I mean, how hard could it be? Any questions? All right, here's an example of one of the quizzes that's going to show, the next quiz that's going to show up. It's going to be more fundamental thermodynamics. Can't remember what I called it. And I give you the graph of the derivative, but I don't tell you it's the graph of the derivative. I just say, here's the graph of a function. And then I use the second fundamental theorem of calculus to define an antiderivative. Then I ask you all the questions about the antiderivative. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day and thanks for playing.